Okay, perhaps we can begin now.
Sure.
Okay, so welcome everybody to this week's Majorana-Raychaudhuri seminar series. Today's first speaker is Lucas Pinol from Paris, and he's going to talk about one-loop freezing of zeta and renormalization of the EFT of inflationary fluctuations. So maybe I'll send you a reminder when 5 minutes are left.
Yes, because to be exact, how much time do I have exactly?
About 45 minutes.
Okay. Thank you for the invitation to give a presentation in this interesting seminar series. So good morning to everyone in Europe. Good afternoon to those of you who are in Asia. So I'm Lucas Pinol. I'm a CNRS researcher based at the physics lab at ENS, which is in the center of Paris. And today I'm glad to present the results of 2 hard years of work with my collaborator, Matteo Braglia, who I also see online, related to loop corrections and renormalization in the framework of inflation. And in particular, we'll focus on the late time behavior of zeta, which is a curvature perturbation during inflation at the one loop level. So let's just start by setting the big picture. So I will be focusing on the inflationary period, which is, as you know, the earliest epoch in our universe that we have a bit of grasp on, which is followed by reheating, and inflation describes the birth of the cosmological fluctuations that we observe in our universe today, both so-called scalar fluctuations, which we can understand as being the density fluctuations, and the primordial ones will be denoted by zeta in this talk, but also the tensor fluctuations, or said otherwise, the gravitational waves, which will be denoted by gamma in the talk. So I see that the audience is all aware of those things, so let me be very quick, but as you know, it's the observation of the CMB that motivated the introduction of inflation as a scenario for the very early universe, and in turn, inflation has predicted the presence of very tiny anisotropies in the temperature and polarization in the CMB before it was even detected, which is one of the great successes of inflation. So I like to argue that inflation is a very unique framework in the sense that it requires, on the theoretical side, both the knowledge and the use of general relativity and quantum field theory. And on the experimental side, we have access to very high precision data, as you can see, for example, by the measurements, very precise measurement of the amplitude of this primordial curvature fluctuation zeta in the CMB. And something very unique of inflation too is that it is sensitive to what happened at very high energy scales, just because the universe was so dense at that time. So here is a very simplified scale of scales in physics. So we have the term the Planck mass at which we expect gravity to be fully quantum. The standard model scale is at the bottom of this ladder here, which is where we have access to experiments on Earth, in particular physics. And the scale of inflation is not exactly known yet, but we expect it to be closer to the top than to the bottom of this ladder. And anyway, something important is that inflation is anyway sensitive to physics up to the Planck mass. And this is actually a formidable opportunity to test the physics at very high energies beyond the reach of what we can do on Earth with cosmology and with cosmological data, which is already very precise and will be even more precise in the future. And those observational probes of the early universe, as you know, are the cosmic microwave background and the large-scale structures mostly so far. And there is a hope, of course, that in the future, the observation of primordial gravitational waves could teach us more about the early universe physics. So as a theoretical cosmologist working on inflation, the objects of study are the primordial correlation functions. So for example, the 2-point function of the density fluctuation, zeta squared, or the one of gravitational waves, or the higher order correlation functions, such as the cubic order, which is related to the primordial bispectrum, etc. So this is very, very, very broad introduction. Sorry for being so boring, but let's go now into the content of the talk. I hope there is a bit of meat for different kinds of interests. So first, I will start by introducing the matter of secular divergences in a relatively thorough way. And then I will turn to the core of the work that I wish to present. First, defining properly the framework in which the loop calculation will then be performed. But first, let me go a bit broad and start with the introductory part. So before starting technical matters, I just wish to have a short historical detour and remind you that it is in 2005 that Weinberg beautifully explained to us poor cosmologists how to do proper QFT calculation even in a curved space-time without having an out vacuum state and using the so-called in-in formalism, which was already known and widely used in other fields of physics, such as out of equilibrium statistical physics, condensed matter, etc. And in those communities, this formalism is rather called the Schwinger-Keldysh technique, and it is exactly the same. Then, in a sequel to this seminal work, Weinberg proved, based on the behavior of the free mode functions during inflation with an attractor phase, that the maximum power of the scale factor A of t that can appear in any correlation function evaluated at the same time p. So for any correlation function and for any number of interaction Hamiltonian inserted in formalism, well, the maximum power of the scale factor is at most 0. And so this is actually a very important theorem which says that correlation functions cannot grow exponentially with time. So what could be left? The only time dependence that could be left at the late times, I'm talking about late time dependence, so is logarithmic time dependence, right? And this is what we call secular divergences because they grow linearly in time, logarithmically in terms of the scale factor, and therefore it's kind of a slow drift of the correlation function at late times. So then the question is, would that possible time dependence be bad? And here Weinberg already notes in 2006 that in generic theories with n integrals, so n insertions of the interaction Hamiltonian, you may find a correlation function at the time t which grow as the log of a to the power n. And then he comments that, of course, such a power series in log of a, if you go to large n, could easily add up and compete with some exponential time dependence, or even worse. So then another question is, are those secular divergences common? Do they actually appear? Because the theorem of Weinberg just says that those can appear. There can be a single power of log of a per interaction Hamiltonian insertion, but it's not necessarily the case. So first, if you have massive mode functions in your in formalism instead of massless mode functions, then they decay faster than the scale factor to the power 0, and this regulates the time integrals in the sense that your correlation function is finite at late times and there is no secular divergence. This is also achieved by the presence of derivative interactions. If your interaction Hamiltonian includes only derivatives of the fields, so for example, time derivative cubed or spatial derivative squared, etc., of the fields, then that will introduce additional negative factors of a in the time integrals, and again, that will regulate the integral, and you will get no secular divergence anymore. So basically, secular divergences are mostly relevant to massless fields with non-derivative interactions. So that's the case, for example, for a test scalar field in de Sitter. We'll go back to this example. Or also possibly to mixed interactions where you have some interactions which have both derivatives and non-derivative fields in the operators. So that's the case, for example, for gravitational interactions, as we are going to see. And an interesting thing is that Weinberg already comments that it would be interesting to see if the power series in the log of a, so if it's really there in the cosmological correlation functions, if this power series can be resummed into a complete time dependence that is physically relevant. And that's indeed the case in one particular example, which is stochastic inflation, and more precisely, the stochastic formalism for scalar fields in de Sitter. So here I will consider, just for the sake of pedagogy, a test massless scalar field chi, which is minimally coupled to gravity, but has this non-derivative self-interaction lambda chi to the 4, and it is in an exact de Sitter background. Then we know how to compute the two-point function at the loop level. Savis and Woodard computed it in 2005. And you can also compute it using a different formalism, which is called this stochastic formalism. And this Starobinsky and Yokohama, who are cited in the next slide, already computed this loop correction with the stochastic formalism in the 90s. And indeed, you get this kind of secular divergence that was mentioned by Weinberg as a mere possibility. And you actually find a power series in these log divergences with higher order divergences as you go to higher order in lambda, which is the interaction strength. And actually, something interesting that I understood recently is that you can get any order in lambda, and we did get in this paper closed form formula with any order in lambda for the two-point function of chi, which is this lambda chi for interacting scalar field. And something more you can get with stochastic inflation is to get the equilibrium result. And this again was already found by Starobinsky and Yokohama in 1994. And something interesting that I understood also in this paper with my collaborators is that you can do a bit more than just looking at the power series and looking at the equilibrium value. You can actually resum this power series, just as Weinberg was suggesting. And we did explicitly this resummation using the so-called Borel technique. And then what you can get is this kind of time dependence of the two-point function, which at early times indeed looks like a secular divergence with just the first term being relevant. But then at later times, all terms in the series become relevant, and you really need to resum this series, which is non-trivial because it's a divergent series, and that's why you need this Borel resummation. And then you can really get the full time dependence, and you can observe that you reach the same equilibrium value as the one that you can also guess just from the equilibrium PDF. Anyway, this is just to say that there are examples in physics and in cosmologically relevant scenarios where secular divergences are present and they have an effect and they can be studied, and that's just the dynamics of the system. And so the question here is, does the curvature perturbation, not a scalar field, not a test scalar field, but the real curvature perturbation zeta, develop such secular divergences in the context of inflation? And that's a matter which is related to the stability of de Sitter spacetime. Because if there is such kind of secular divergences, it could mean that the de Sitter is unstable because fluctuations would grow large. So first, we know that classically and at the linear level, that's not the case. From the work by Mukhanov and Sasaki, for example, you know that the fluctuations at the linear level, they converge to a super horizon constant value, and therefore there is no such kind of secular divergences. Then Maldacena showed that even taking into account the first nonlinear classical correction, which is a cubic interaction, all cubic interactions during inflation, that the three-point function, the bispectrum of zeta, was also convergent on super horizon scale to an asymptotic value, which I noted here as b zeta 0. So there is no secular divergence neither in the primordial non-Gaussianities so far. And then the question that we want to address in this talk is the first nonlinear but quantum correction, that is the first loop correction to the two-point function of zeta, coming from this cubic or quartic interactions, as we are going to see. So at the linear level, we have the tree-level prediction, which again, as we know for a long time, has no secular divergence. But the question is, does secular divergence appear at the loop level? And then we can just imagine a world where this does happen. Then you would actually get these instabilities of de Sitter, and if inflation lasts for a long time, the close to de Sitter background would actually be spoiled by the growth of this fluctuation. And actually, this could not necessarily be a very bad thing because it could also provide a natural end to the De Sitter epoch and a transition to something else. So that would be something interesting. But in any case, that would signal a breakdown of perturbation theory because it would mean that fluctuations grow so large that the background you've been assuming is not valid anymore. So then you would just need to find another framework to make your calculations because the one that you have been using would be wrong. And maybe more negatively, it would imply a loss of predictivity for inflation. And this is something very important. But if the curvature fluctuation is not conserved anymore at the loop level, even on super horizon scales, then there is no adiabatic limit. That's the definition of adiabatic limit, which is not verified here. And therefore, the predictions of inflation would heavily depend on what happens during reheating and the whole Big Bang cosmology, like BBN, etc. So that would be something to address, right? So we can already start to list the difficulties on the route to this calculation of the one loop power spectrum for zeta. So first, the complication is that we are dealing with gravity here. It's not a test scalar field, but it's the curvature perturbation, which is coupled, which is a gauge invariant quantity that is related both to field fluctuations and space-time metric fluctuations. You also have constraints in general relativity that in principle must be solved. And as I was mentioning in the beginning, gravitational interactions are of the mixed kind. For example, you have this zeta dot squared interaction. You even have this anti-derivative interaction, etc., which a priori can lead to secular divergences. So we need to be careful about those things. Also, the background space-time, which is close to the Sitter during inflation, can have some back reaction corrections from the fluctuations. We need to account for this effect. And we will have to deal with all kinds of possible divergences here. So the secular divergences that I have explained before, but also the usual divergences that you can get in quantum field theory, which are the ultraviolet divergences at the loop level and the infrared divergences. So the matter is that we want to address all those conceptual and technical difficulties at once. And for this, we chose to use the framework which is called the effective field theory of inflationary fluctuations because we realized it was really an exceptional framework to address all those questions at once. First, it enables a model-independent formulation for the fluctuations and their interactions. You can describe the dominant gravitational effects, as I will show, even using the so-called decoupling limit, which has been put forward in the past. And you can also perturbatively renormalize your effective field theory because it's an effective field theory. And this, even though GR itself is of course a non-renormalizable field theory. And as I will show, the effects of symmetries, of background spacetime symmetries, and how they are realized are made manifest in this framework, and this has very important consequences for the results and for the calculation itself, as I will show. Okay, so because this is so important, and I want to spend a bit of time to motivate the framework in which I will do the calculation. So actually, an important part of the presentation and of the papers that we published on this topic are related to the understanding better the effective field theory for inflationary fluctuations. So first, what happens is that inflation breaks the time translation symmetries of the De Sitter spacetime by making the scale factor h dynamical. So that's the usual story in cosmology. We have a time-dependent background that breaks this possibly maximally symmetric spacetimes. And therefore, we can expect to have an non-Googlestone boson related to the breaking of this diffeomorphism invariance. And then what we want to, the game we want to play is that we want to build an effective field theory which respects the residual symmetries of our background spacetime, which is not anymore the full four-dimensional diffeomorphism invariance, but which is broken to having only the spatial diffeomorphism invariance. And therefore, we can use building blocks in our EFT which violate Lorentz symmetries. So in particular, we can use the metric, of course, the full four-dimensional metric, but we can also use metric components which are evaluated with which have one index evaluated on the time components. For example, this G0 mu, or even more this G00. So for example, G00 and G0 mu, they are not covariant under time reparameterizations, so they violate this time translation symmetry as we wish, but they are invariant under the spatial diffeomorphism. Okay. Then it's useful to categorize the different quantities that can appear in the EFT to use 3+1 decomposition of the metric, so the so-called ADM formalism, in which you see the appearance of the spatial curvatures, the three-dimensional curvatures, so the extrinsic curvature K and the intrinsic curvature R. So we can also use those quantities in the EFT. And then, of course, you can use derivatives of all those quantities and any function of time, which would be some kind of background function of time, since, again, you can break time translation symmetry. Okay, so building a Lagrangian with these blocks corresponds to working in a so-called unitary gauge, because the Nambu-Goldstone boson is not explicitly present. Actually, the Nambu-Goldstone boson is hidden in the metric, so it's hidden in the gauge sector. So in 2006 and 2008, it was systematized. It was shown that the most general unitary gauge Lagrangian compatible with a Friedmann-Lemaitre-Robertson-Walker background metric is the following one. So you recover the Einstein-Hilbert term of general relativity, and you have some of these functions of time that I was mentioning, which are fixed by the requirement that the background is FLRW. Then you have all the remaining freedom in your EFT, which is encapsulated in this function F2, which you can show can be written in terms of those quantity only, the delta G00, the perturbation of the 00 metric, delta Kij, delta Rij, etc. And here F2 starts quadratic in the fluctuations. Okay, so this doesn't have any one-point term or any background or any function. Okay, so then what we want to do is that we want to organize our EFT, and we want to have some rules to decide which of the possible operators, because there are many, which of them are the most relevant for the system we have at hand. And here we rely on the usual rule in EFT, which is the derivative expansion, which I quickly explain here. So the idea is that we will assume that there is a single energy scale lambda at which new physics may enter. So if you want, we have an assumption about the UV completion of the EFT, which is that there is a single scale lambda that describes this UV completion. And then you can show that higher number of derivatives operators, they will bring higher powers of h over lambda in any of the observable. And therefore, if you work at energies h much smaller than the cutoff of your EFT lambda, you control the corrections, you control the derivative expansion, and those can be taken into account consistently as corrections to the lowest order. And then you can truncate your EFT to some derivative order depending on the precision that you seek for your observable. So say, for example, you want to have a precision of order h over lambda squared in your observable, then you can truncate your EFT at the two derivative order more than the lowest possible operator that you can write. So what are those possible operators? First, there are some operators which appear already at the non-derivative order. There is no derivative at all. And this is a tower of operator with any power of the space-time fluctuation delta G00 with some coefficients mn, which can depend on time. Then you can go to higher orders with one derivative term, such as this one. For example, the extrinsic curvature delta k has one spatial derivative. So this operator has just one spatial derivative. And then all the other ones are examples of two derivative operators. Okay. So just to show exactly how it works, suppose there is this unique scale lambda. at which new physics enter, and suppose all the derivatives are evaluated around the time of horizon crossing for inflation. So that would be at an energy scale of order h. Then delta k, for example, is order h times the typical fluctuation. Delta r is order h squared times the typical fluctuation. And you can show that there is indeed hierarchy in the h over lambda expansion between the different operators. And you see that higher derivative operators are indeed more suppressed by lambda than the non-derivative one.
Lucas, I have a question.
Sure.
Why do you have to compute that horizon exit?
No, you don't have to. Here it's
As
here
an
is just
example you were giving.
no, yeah. You will see that when we do the real calculation, we don't do that. We use the complete operators and we integrate over time, we integrate over the momenta, and we take everything into account. This is just more like a naive power quanting, if you want, of the different operators, but that works in practice. I will show the different contributions and the h over lambda order that they result in.
Okay, I thought so. I just got confused. Okay, thank you.
No worries, no worries. And of course, I should have said it at the beginning, but please interrupt as much as you'd like. It's more fun for me, especially that I don't see any of you. In this series of two papers, what we did is that we started with an EFT which is truncated at the leading non-derivative order. So we will keep only the non-derivative operators at this stage. You will see that actually higher order in derivatives operators will be generated by our renormalization procedure, as you could guess. But for now, let's just truncate the EFT at non-derivative order, which is the leading order. And then, just for technical simplicity, we will fine-tune the theory by setting M3 and M4 in this infinite sum here to 0. So that will mean that F2 will just have the delta G00 squared term, and then possibly higher orders that orders larger or equal to 5 that will not be relevant for the loop calculation the one loop calculation that we are after. So then what you can do is that you can make appear explicitly the Nambu-Goldstone boson that I was mentioning. So far we are in the so-called unitary gauge, where the scalar degree of freedom, which is propagating, which is dynamical during inflation, which is the adiabatic fluctuation that we always have in cosmology, is hidden in the metric so far. So what we want to do is we want to extract it from the metric, and in particular, we'd like to extract the dominant interactions of this fluctuation. Okay. So now F2 is very oversimplified to this single operator, and we use the so-called Stuckelberg trick to introduce explicitly this Goldstone boson pi. And the idea is that you can restore diffeomorphism invariance in your Lagrangian, which breaks the time part of it, by redefining time as a space-time dependent quantity. So you redefine your time to a local time, which is t plus pi, such that this t plus pi is itself invariant under the full four-dimensional diffeomorphisms. And when you do so, you extract the pi degree of freedom of your Lagrangian. And something which is sometimes not mentioned, but which is quite important, is that there remains a gauge degree of freedom, even in this using this Stuckelberg trick. And so what we do explicitly here is that we work in the flat gauge, in which case you can show that the Goldstone boson pi in the flat gauge, which is written here as pi, is related to the curvature fluctuation zeta that we are usually interested in cosmology by the following relation, and it goes to higher orders that we will not need here. So what you can do is that then you just need to look at how all this Lagrangian transforms under this time reparameterization. And so, for example, here I show how the perturbation of the 0,0 component of the metric transforms under this time reparameterization. And here you see that it transforms in a non-covariant way, which is because delta G00 was not covariant under full diffeomorphisms. So what's important is that you get some terms which are both linear and quadratic in pi, but you don't get any term which is cubic in pi or higher order, for example. So this is an exact expression. There is nothing else. It's not truncated to any order. And this is a manifestation of this so-called non-linearly realized symmetries, which is inheriting the diffeomorphism invariance of the initial theory, which is just the sitter. And so, for example, you need to replace, for example, here you have h in the Lagrangian, you need to replace it by h evaluated at t plus pi, and then you can expand in pi, and you get a Lagrangian for pi, and you do this for every single block in this EFT. Okay, I need to go a bit quicker, I think. So something important is that a priori you also need to solve for the lapse and the shift, which are the constraints which do appear even after reintroducing this Goldstone boson pi. And if you want to solve them, you can solve them, for example, at the linear order. You can find that delta G00 flat, which is a lapse, can be related to pi via this simple relation. But actually, what I would like is that I would like to neglect the constraints to make it simpler. Again, this is just a technical simplicity. It's not absolutely required conceptually. And I can just look at the condition to be able to neglect the lapse and the shift in my Lagrangian. And I can show that if I want to neglect delta G00 flat here compared to pi dot, for example, I need the energy at which I am probing my experiment to be such that its square is much bigger than epsilon times h square, which means that at high enough energies, the Nambu-Goldstone alone describes the whole dynamics. You don't need to solve for the constraint at high energies. And of course, what you'd like is that these high energies are not too high, because you actually want to go down to the Hubble crossing for your fluctuation, right? So in particular, if you want to use the decoupling limit around horizon crossing, which happens when omega is roughly h, then you see that you need h squared to be much bigger than epsilon h squared, which means you need epsilon much bigger than 1. So you have this kind of range of scales in which you can trust your EFT. Note that this decoupling limit brings no constraints so far on eta, which is a logarithmic time derivative of epsilon, and the higher order derivatives of it. Then, of course, when you cross the horizon and you go to very, very super horizon scales, at some point the decoupling limit will break down, of course. But that is not a problem, because if an adiabatic limit is reached before that, then zeta has reached a constant, and you can just propagate the predictions to the end of inflation. So that's the hope. Okay, so that's just a quick summary. We start from the most general Lagrangian compatible with symmetry. We have a single assumption about the UV physics, which is that there is one energy scale lambda. We do a bit of fine-tuning just for simplicity, and also use this decoupling limit also for simplicity. Then what we get is the following Lagrangian at different order in the fluctuation. So at quadratic order, we find the Goldstone boson pi with possible speed of sound, CS, which is between 0 and 1. And at the cubic order, we find the following interactions. So some of these interactions are directly related to the speed of sound, like the F0 term, for example. You see when the speed of sound is 1, it disappears. Same for F1. F2 simplifies a lot in this limit 2, etc. And some of them don't. And for example, this F3 interaction has nothing to do with having a speed of sound. And something which is interesting is that this Lagrangian that we find with our EFT in the decoupling limit, it actually matches the cubic Lagrangian for fluctuations in so-called general single field models, so the P of X and phi Lagrangians, in the limit that epsilon is very small. So we get the leading epsilon cubic interaction of P of X phi Lagrangian, which happens actually to be also the same as the effective Lagrangians that you get in multifield inflation once you have integrated out all the heavy fluctuations in your theory. You also end up with a Lagrangian of this form. Okay? So this EFT can encapsulate, so let's say those are candidate UV completions to this EFT for fluctuations. But what's more is that with the EFT, we can also easily get the quartic interaction. And this is something which is very non-trivial to do with covariant models such as P of X phi Lagrangians or multifield Lagrangian. Actually, it was never done. But with the EFT, it's relatively straightforward. I mean, it's a bit of calculation, but it's relatively easy to get the quartic interactions too. And again, you see some interactions are proportional to 1 over c squared minus 1, and others don't. So just to summarize, what we have so far is an EFT for the adiabatic fluctuation. We have the free theory, which gives you the propagators in your theory, which are given by the free field mode functions written here with the speed of sound CS. You have some cubic interactions, which are given just by minus the Lagrangian. And here I will simplify a little bit the cubic interaction, and I will just take the ones that survive in the limit that CS squared goes to 1. So remember, we have several interactions, like F0, for example, will go to 0 when CS squared goes to 1, and others will survive. Why do I take this limit? It's just because, again, I want to have a little bit less diagrams to compute later, and that the ones that I choose to keep are actually the gravitational interactions. Those are the ones which are proportional to eta, and which lead, for example, to this consistency relation in single field inflation that FNL in the squeeze limit is given by minus eta, basically. And at the quartic level, I play the same game. I just keep the interactions that survive in the limit c square goes to 1, and I find the following quartic interactions in the Hamiltonian. Okay, so now I want to perform my loop calculation, and I want to see what happens with the different kinds of possible divergences. So I can organize my loop calculation with diagrams where I can put cubic insertions, either time derivative and spatial derivative interactions in black and white dots here, and I just take all of possible ones in count. Also have the quartic interactions, so I also need to sum over these diagrams. And something interesting is that all these diagrams taken separately are divergent in the infrared, divergent in the ultraviolet regime, and also secular divergent. So they also have these late time divergences that Weinberg noted could appear. So what we want to do is that we want to compute everything. So we cannot just sum infinities and see what happens. So what we need to do is that we need to regulate all those divergences in order to be able to keep track of them and just add them, for example. So what we do is that we introduce a co-moving infrared cutoff. That's for the IR divergence. I will not spend a lot of time about the IR divergence because that was not the topic of this works, but I'm just mentioning it for completeness here. For the ultraviolet divergences, what we do is that we use dimensional regularization. So we go to d equal 3 plus delta spatial dimensions. And for the secular divergences, I will just introduce a finite external time, tau, at which I compute my correlation function. I will not take it directly to be the end of inflation. I will regulate it by a finite time at which I compute it. And I will use this conformal rescale time x, which is minus k tau. So dimensional regularization, of course, complicates the calculation because both the mode functions are different in the 3 plus delta spatial dimensions, and also the integral measure that remains in the loop are different. And this is the reason why we use dimensional regularization, is that then we have this factor k to the power d minus 1, which regulates the UV divergence. So now we can compute the loop contribution, and for this we use a strategy which was presented first in this paper by Senatori and Zarega. We also use a trick that was proposed last year to compute explicitly all the divergences, but also the finite terms in the loops. And to flash the final result, what we get is the following: the bare contribution, which is the sum of all these diagrams, is given by both ultraviolet divergences, infrared divergences, and some terms which we call finite here in the sense that they don't have any UV nor IR divergence. However, this is a UV divergence, and you see it has this 1 over delta, right? And this is the important piece. And indeed, when you take the limit delta goes to 0, which is our real universe, then you find infinity, of course. So you have a UV divergence, and something important is that this UV divergence is time dependent. You see that you have this minus parenthesis 1 plus CS square x squared. Okay, so this is a time dependent UV divergence. I will skip the IR part because I don't want to discuss it here, but we also have the part which is finite in the IR and the UV. But when you take the limit that x goes to 0, so this is the end of inflation limit, you find this log x divergence, which is the secular divergences that we were mentioning. And something important to mention here is that this is the sum of all the individual diagram secular divergences. So the sum of all of them is not 0. So it seems that there is some secular divergence that remains. But let me first make a little detour to the UV divergences. So what we want to do is that we want to absorb the time-dependent UV divergences.
We have 5 minutes left.
I have 5 minutes left. That's almost good. I need 7 minutes. Okay, I'll try to be a bit quick. So what we want to do is to absorb the UV divergences with counter terms. So for example, you can try to do it with renormalizing the speed of sound. Remember, we have this operator for the speed of sound at the quadratic level. You can try to renormalize it and have some renormalization coefficient delta. And then this adds a counter term to your theory. and you find the following quantity. Okay, so now what you'd like to do is to use that to cancel the UV divergences, but actually see the time dependence of this counter term is not the same one as the time dependence of the UV divergence. Here you have -1, here you have +1. And therefore, this means that you cannot use the speed of sound counter term to cancel the UV divergences at all times. What you can do is use the speed of sound to cancel it at the time x equals 0, so the end of inflation, that works. But it's not satisfactory. We don't want to have UV divergences at all time except at the last time. This is a very peculiar framework that we don't want to have. So what you need to do is to go to higher order derivatives. And this is where, as I was mentioning at the beginning, the EFT is useful because we can just categorize what are the higher order derivative operators and see their effects, on our two-point function. So now we have additional counter terms, this delta 1 and delta 2, and we can look at their effects. And this time, something that you can notice is that if you just take this time dependent minus this one, you just find 4 times 1 plus c squared x squared, which was exactly the time dependence of the UV divergence that we had found in the bare loop contributions. And therefore, you can just choose the size of the coefficients delta 1 and delta 2 such that they cancel the UV divergences at all times. So this is what we do. We fix delta 1 and delta 2 such that the UV divergences are fully cancelled at all times. So now we are done with the UV divergences. We have renormalized this part of the theories. However, the finite terms that come from these UV divergences are fully finite in the limit x goes to 0. So therefore, the secular divergences that we had in the bare loop, they are still there. They remain. Okay, so this is still something we have to deal with. And now the interesting thing is that we have to realize that we forgot a set of diagrams, which are the so-called tadpole diagrams. And here we follow the steps of Pimentel, Senatore, and Zedaraga, who first noted that with different interactions in the EFT of inflation. And they realized that because of the cubic interactions, the perturbation theory is not defined anymore around the true vacuum. No, you actually backreact on the background spacetime. So you need to take that into account. You want to shift your perturbation theory so that backreaction is taken into account. And now you are really defining your theory around the correct vacuum. So in order to do that, what we do is that we introduce one-point counter terms in order to cancel these tadpole divergences. So of course, So of course, what we need to do is that we want to respect the symmetries of our EFT. So we need to use operators which verifies spatial diffeomorphism invariance, right? We write the possible operators that could lead to tadpole terms, and we indeed find that you can add this one-point interaction with delta lambda dot and delta c, which become fully fixed by the requirement that the sum of these diagrams exactly cancel. So now, thanks to this tadpole vanishing, we are really defining our perturbation theory around the true vacuum, and in particular, we showed that all the so-called non-one particle irreducible diagrams of the theory, they cancel. So for example, in the two-point function, you can draw these weird diagrams, and you can show that if this is verified, then all these diagrams also sum up to 0. But then something important to realize is that because of the nonlinearly realized symmetries of the EFT, and because of the Legendre transform between the Lagrangian and the Hamiltonian in the theory, you also necessarily induce some quadratic terms in pi squared and pi dot. But this time, the function delta lambda dot and delta c dot and delta c that appear here, they're already fixed. You cannot use this anymore for anything. It's not, you don't have any freedom on those quantities. They are just fixed. And they give interactions which must be taken into account. So we have to add this to the power spectrum. We have no other choice. We need to do it, right? And when we do this, we just look at the limit at late times of this contribution, and we find the following, which has some secular divergence. Now, remember, the bare contribution had this kind of secular divergence with this exact coefficient. Now, the counter term, which are induced by the tadpole cancellation, have these contributions. And as you must have noted, there is just a minus sign between the two. And then, therefore, when you sum them, the secular divergences just cancel. So the total result that we get is the sum of the bare contribution plus the tadpole-induced counter terms, which are fully fixed by the requirement to work on the perturbation theory defined around the correct vacuum, plus the UV counter terms, which are used to cancel the UV divergences at all times. And when we do so, we find that the one loop power spectrum of the Goldstone boson pi is conserved at the super horizon scales. And this in particular, thanks to these terms, which are induced by these non-linearly realized symmetries. And the final result is the following. You can look at the renormalized power spectrum of pi divided by the tree level, and you find that the correction is indeed suppressed by h over lambda squared, where lambda are the strong coupling scales associated to the interactions that we have been considering, which are nothing but the cubic and quartic gravitational interactions that are dominant during inflation. And then what we can do is that we can safely match pi to zeta on the super horizon scales and derive the renormalized power spectrum of zeta and find that there is no secular divergence in it. So this is the conclusion. We have a successful perturbative renormalization of the EFT of inflation at the order h over lambda squared. So just to mention very quickly, we did two extensions of this calculation. First, to the loop induced by the scalar on the tensor two-point function. We also computed the tensor two-point function at one loop and renormalized it. And we found that this time, even the Baire contributions were finite at the latents. There was no secular divergence when you sum over these two diagrams. And this is indeed expected because in that case, there cannot be any tadpole. There is no tadpole with just one tensor. This is forbidden by the FLRW symmetries. And we also have the UV divergences that are cancelled at all times. We also did it for a first example of a multi-field scenario where we considered the EFT of inflation a little bit extended to admit additional particle content. And this is something that has been developed in particular in these three papers. And there you can also organize your EFT multi-field interactions and according to the EFT principles. And we also computed the loop and also renormalized it. And this time we found that you have to renormalize the speed of sound to cancel the UV divergences. Okay, that's the final slide of my talk. Just to mention that all the cases that we have been focusing on in these two works are scale invariant scenarios. And therefore, there is a running in the loop, but this running takes the form of log of h over mu, where mu is the so-called renormalization scale of the theory. And therefore, the running is not really observable because it's not like we can change h. There is nothing that we can run with, basically. So this motivates the extension of this work to strongly scale-dependent cases. So for example, to the scenarios which can induce interesting phenomenology at the small scale, such as primordial black holes and gravitational waves. And then there are some technical assumptions that could be relaxed. I think that would be interesting. And so we could explore, of course, more scenarios. So, okay, let me stop here. I'm 2 minutes late. Sorry for that. Thank you for listening to me.
Okay, thank you for the nice seminar. Anybody anybody in the audience want to ask question? Please unmute yourself and ask.